Hi, my name is Krzysiek Rządca. I work as a data scientist at Google, and I will be presenting our paper on Efingo, a large-scale batch copy service with Michał.
Hello, I'm Michał. I'm the engineering manager of Efingo, part of Google Storage.
So let's start with a typical transfer story. Alice has a movie, and Bob wants to see this movie. The problem is Alice lives in Alice Springs in Australia, and Bob lives in Brussels in Belgium. And the geographical distance, but also the network distance is huge. So a standard way is that Bob issues a standard HTTP GET request to get the movie, and then Alice transfers the movie back to Bob. This makes sense when the transfer is when there is one transfer. But let's say Bob likes the movies so much that he throws a party and has a lot of guests that want to see the movie. And as you may imagine, repeated transfers between Australia and Belgium are not cheap because they heavily use expensive undersea cables. So the standard solution is pre-caching of the content that can be popular. Bob uses SCP to get the file from Alice, cache it locally, and then serve the request from its local copy. Another popular use case is that Alice has lots of movies from her, let's say, from her childhood, and she wants to run some ML models. For instance, to find the movies where Uncle Bob appears. And Uncle Bob in Brussels happens to have an idling GPU server. Again, one possibility is that Uncle Bob puts the server in a shipping container, and the container gets shipped to Alice Springs, and Alice uses then the server locally. The problem is it takes at least 6 weeks to move a container between Europe and Australia. The alternative is again move all the movies to Brussels to Bob so that Bob can process the movies locally. So in both cases, SCP was sufficient to get the to cover Alice and Bob's needs. Thus, where are we here? Why and when SCP is insufficient? So rarely, in reality, as a cloud provider, rarely we have a simple transfer of a single file between two locations. First, we heavily use redundant storage so that we are more immune to failing hardware, failing disks, failing servers. So each file is stored on multiple physical servers and multiple physical disks. And moreover, file replication strategies might differ between sites and file systems. So Alice might use something like RAID replication, while Bob can use standard 3 times replication. One-to-many transfers are common too. So say Alice has not only Uncle Bob in Belgium, but also Uncle Claude in Canada and Uncle Dan in Denmark. And Alice wants to send the movie to these 3 locations at the same time. As you can imagine, transferring data between Australia and Belgium and then Australia and Denmark might be redundant because, again, we heavily use these expensive undersea cables. So perhaps we want to route these requests so that files are first transferred to Belgium and then using local local networks to Denmark. The problem is routing might dynamically change in time. There are situations where this Australia, Belgium to Denmark routing is more efficient. But there are also situations where we would use the broad bandwidth between Europe and North America to transfer first to Belgium and then to Canada. And also, there can be situations where, for instance, Belgium-Denmark link is heavily utilized or down, and we would use separate transfers to Belgium and also directly to Denmark. On the other hand, let's say we have an uncle, we have a cousin, Jan, in Iowa, and there is an unofficial family policy never to share sensitive content, never to share perhaps sensitive videos with Uncle Jan, because Uncle Jan, everything we share with Uncle Jan tends to end up on trending on TikTok. So there might be some policies that, even though routing would be more efficient between between Australia and North America, and then North America to Europe, we would rather use direct. We would not use third clusters to store the data in transit. Finally, this system is highly heterogeneous. In reality, each side is composed of at least 3 independent clusters. And moreover, these clusters come and go dynamically. So older clusters tend to be decommissioned. Newer clusters tend to be brought up. And our system has to dynamically handle this changing topology, changing communication graph. Finally, the system is highly dynamic. On a typical day, we have thousands of users. We have billions of files per day and an exabyte of data that is copied. So this translates to many transfers that are happening in parallel. And there is a huge performance inference on the network links, but also on the egress and ingress bandwidth, the I/O between computation, between disks and nodes, and the network links.
Okay, and here we've got our Google answer. At global scale, it's Efingo. That's a simple service. A user can just say, copy my file from cluster A to cluster B, indicating the paths. Copy done. Okay, so some of the characteristics. Efingo operates on all Google clusters, and a client can be anywhere. The same with data. That means we can have like 3 clusters engaged in a copy, a cluster where a client is, then the source cluster, and the destination cluster. We've got wide spectrum of users. There are users that perform batch operations, replication, data over the planet to reduce the data access latency. There are also latency sensitive use cases, copy the data like in sub minutes. And we've got many other like complex scenarios, for instance, where users have their own scheduling mechanisms, and that can complicate things with our backlog. Everything is with like cluster level failure domain, meaning that there's no any global component or cluster not engaged in a copy that failure can cause a particular copy to fail. We copy as fast as possible under SLO coverage, but also we provide functionality to copy in best effort mode without SLO coverage. Architecturally, Fingo is split into control plane and data plane. Control plane orchestrates a copy request, and data plane is actually engaged in the bytes transfer. And Fingo supports variety of Google internal file systems. So here we've got an example of copy request. Same colors indicate same cluster. So we've got a client in some blue cluster ZZ. A client says copy data from yellow cluster YY, indicating file 1 txt to the green cluster XX. Transfer manager validates copy request. It persists a valid copy request and then orchestrates entire copy. Of course, we copy as fast as possible, so a file is copied in parallel in transfer chunks. And then transfer manager orchestrates and executes actual transfers of each transfer chunk. So request goes to destination manager that finds and allocates destination worker. And also destination manager is responsible for finalizing the copy once it's done. We've got also source manager engaged that finds the source workers, and then source worker actually having the destination worker address initiates the byte transfer that goes through like at the physical layer, it goes through some fiber optics that needs network bandwidth. Also destination workers and source workers, they need compute power to read and write data in parallel, and also do some transcoding or some basic calculations while transferring the data, for instance, checksum. And of course, every data read and write uses storage. So at every site, we need to allocate resources to I/O ops. Here we are showing the scale at the aggregated level, all users, all locations. So typical day with Fingo is more than 1 exabyte of data in volume. We've got aggregated transfer rate like from 10 to 20 terabytes per second. It's about thousands of users spread across the world. Some users copy like to majority of the clusters. Some just use a few clusters in their copy. The highest peaks we observed so far, and we dealt with them, were about 200,000 completed copies per user per cluster. So we'd like to share like how do we provide this maximum throughput under very heterogeneous for the heterogeneous storage system copies. So the reality is that every cluster is different. Every cluster has different load, has different hardware characteristics. The same with network bandwidth, and you remember from the first slide explaining the architecture, we also need compute power in workers, processor, and RAM. and we're not having any centralized service saying our workers how fast they should transfer the data. So there are two main transfers. There are two main algorithms. One is incrementing the parallelism on workers and doing back off on errors. And the other is regulating throughput in P feedback loop. So we're adding parallelism independently to the first algorithm when we see it makes sense. So we're not reaching plateau. Otherwise, like we're stepping back. Also, one of the core properties of Fingo and something we're explaining in the paper is fair resource distribution, again with a central oracle. Here is our experiment showing copies from one source to one destination, where these copies compete for resources that are limited. And what we're showing here is a very stable aggregated throughput. Another important characteristic of Fingo is its built-in compliance, and there's not enough exploration of huge decentralized data transfer systems where there's no central component controlling what's happening in the system, and the failure domains are per cluster versus per region or per like load balancing zone. And thanks a lot for your attention, and we're open for questions.